However, I hope it is quite clear to every one of you that nerve cells are individual cells. That is, if you want the information to reach from your brain to your muscles, then information must pass from one cell to the next. This lecture I will be discussing this transmission of information from one cell to the next. And if this transmission happens in a specialized structural form, then we talk about synapses. So the lecture today is about synapses. The information can and does sometimes pass without any particular special structural entity. These are referred to as apopsis. These are not part of physiology lectures. So if you hear this expression somewhere, please note that this is a way of information going from one cell, without any structural things behind. Two nerves going close to one another and influencing each other. Not part of physiology. Synapses. Oops, sorry. This is the Hungarian. Why did you tell me so? Please worry not, I have everything in English as well. So, synapses, this is how you write synapses. Synapses are divided based on the mode of transmission of information. And if that involves an electrical coupling between the two cells, we talk about electrical synapses. If it involves some chemical substance going between the two cells, then we talk about chemical synapses. And in certain cases, in the same structure, both electrical and chemical synapses can be present, then we call them mixed synapses. Please also note that in case of transmission of information from nerves to other nerves in the periphery, or from nerves to other type of cells like muscle, it is usually a chemical synapse. Electrical synapses, or so-called gap junctions, are present in between certain cells in our body, smooth muscle cells, heart muscle cells, and in the central nervous system. Since gap junctions are much less abundant as compared to chemical synapses, I will spend a very short time on electrical synapses just to say a few general ideas of how they work and what should we understand under electrical synapse and gap junction. So if one blows up an electrical synapse, then this cartoon would like to depict what you would like to see. Please, unless I say that this drawing is essential to be known, you do not need to be able to draw those back. So for example, please don't attempt to draw the figure on the left. So, what you should see in this drawing, I hope you do, I do, so I can explain. This would be one membrane here. You see the double bilayer with phospholipids and so on. This would be another membrane down here, okay? And these are two cells. The information, one thing to pass from here down to here. So this guy and this guy has so-called connexon channels built up of 5 identical molecules called connexins. These are these things here. And they form a pore, and the 2 membranes and the pores in these membranes are organized such that the 2 channels are just underneath one another. So they can form a big pore that goes from the intracellular space of one cell to the intracellular space of the other cell. These pores are huge. Not only ions, but small molecules, organic molecules, can pass through these channels. However, they can also gate, that is close or open. And the way we envision how this happens is shown on the right. That is these individual molecules that twist on top of one another. And once they twisted, they form the pore. And then if twisted back, they close. The opening and closing are regulated mostly by changes in intracellular ionase concentration. That is, a drop in pH, or an increase in hydrogen ion concentration, or an increase in calcium ion concentration will close these channels. This is essential because usually dying of cells is associated with such changes, and therefore dead cells become isolated from living cells by these changes, and otherwise the dead cells would influence living cells, and a dead cell that gets depolarized will depolarize all neighboring cells, which would be disastrous if it happens in the heart. So we will see where the heart cells are connected by these gap junctions. So what can we say about gap junctions? Well, this is a very simple, my first funny experiment, where 2 axons connected by a gap junction were taken and currents were injected into the, let's say, call it left and right axon. And what action potentials were prevented from occurring to study what these synapses do. And as you can see, if you inject a current, either depolarizing or hyperpolarizing, what you see is an electrotonic change, depolarizing and hyperpolarizing in the left axon, as you would expect. If you inject current, that is, if you put positive or negative charges inside the cell, then the membrane potential will go positive or negative. Very simple. The trick comes if you look at the other axon, and you see that everything that happened in this axon happens in the other axon. And it happens backwards. If you do it on the right axon, you see the electrotonic changes, and that happened in the left axon as well. Although the change is smaller, so as you expect from electrotonic potentials, they spread with decrement. So these guys transmit information in both directions, and the potential change spreads with a decrement, and essentially without any delay. So when you do it here, it instantly appears in both axons. This is the, let's say, 80% of our gap junctions work this way. The other 20 make it a little more difficult, or a little more complicated, but not much. The same experiment was taken, and as you can see, if you depolarize the left axon, then depolarization appears on the right axon as well. If you hyperpolarize the left axon, that doesn't appear on the right axon. The other way, if you hyperpolarize the right axon, the hyperpolarization appears on the left, but if you depolarize the right, one here called post and pre, I will come back to why this is post and pre, that will not appear in the other axon. So, in some special cases, these electrical synapses, we call it rectified. That is, they only allow the movement of cations in one direction, while the movement of anions in another direction. This is depicted here, where from pre to post, positive charges can go, negative charges cannot, whereas from post to pre, positive charges cannot go, negative charges can. In this case, depolarization, which is usually what we call as the information, can only spread in one direction. This is why I'll call this pre and post, because information in the form of action potential would travel in this direction. This would become activated first, and then this one. So this is pre, and that is post. And that is all I wanted to say about electrical synapses. All the rest of the time that we have, we will spend on chemical synapses. Not only because they are more abundant, but also because the drugs or medication, I should say, that you in your medical practice will subscribe to patients, treating them from cardiac problems to depression and so on and so forth, are targeting chemical synapses. So how does a chemical synapse work? Well, first of all, some general terms that we need to agree upon so that you understand what I'm saying. In every case in a chemical synapse, there is a presynaptic and a postsynaptic cell. Presynaptic and postsynaptic cell. Presynaptic is the cell from which the action potential and the information comes. Postsynaptic is the cell onto which the information goes on. Between the two cells there is a distance, and this distance, extracellular space, we call synaptic cleft. This is a chemical synapse because the information from this presynaptic cell goes to the postsynaptic cell via chemical substances called neurotransmitters. Transmit, take over. Yeah? In order for the postsynaptic cells to detect these chemical substances, they have receptors on them, specific for this particular chemical neurotransmitter. Okay? These receptors are ionotropic, ligand-gated, gated by this particular ligand, ion channels. This is how the information goes from one cell to the next. The chemical synapse is nevertheless, can be, and is influenced by other means. So both the presynaptic and the postsynaptic cell have metabotropic receptors which have modulatory role on how the synaptic transmission works. Very frequently, these metabotropic receptors are found on the presynaptic cell and are target of those drugs or medications that we use. Very rarely, only in certain toxications, do we interfere with this direct transmission. We usually modify the transmission by giving drugs that act on the synapse through these things. This interference is rarely done. This is in cases of toxication. You will see examples later on as I go along. So, please remember, presynaptic cell, synaptic cleft, postsynaptic cell, neurotransmitter. And please understand that by no means can you make the systems to work in the other way. That is, the information will never ever go from the postsynaptic cell to the presynaptic cell in the synapse. There is no neurotransmitter here, and there are no receptors here to detect this non-existing neurotransmitter. This doesn't mean that this cell cannot make a synapse on this cell somewhere else and influence this cell. But in this synapse, the information is always unidirectional. Goes from the presynaptic cell to the postsynaptic. If there is another synapse, that's another synapse, and again there's a unidirectional transmission of information. So, what are the steps that take place during the transmission of information in a chemical synapse? So obviously, an action potential comes along the neuron and reaches this end which sometimes is referred to as a button, if you heard this expression. If not, we will just say that the end of the axon. So this action potential arrives at this end of the axon, and of course this is a depolarization. This depolarization here finds calcium channels, voltage-gated calcium channels, very much like sodium channels. The difference is that instead of letting in sodium, they let in calcium. Calcium ions will then go from the extracellular space into the intracellular space and increase the calcium inside the presynaptic cell. Then a calcium-induced exocytosis of these vesicles that contain the neurotransmitter takes place, and these vesicles move along and migrate and fuse with the membrane of the presynaptic cell. Then the neurotransmitter is released and appears in the synaptic cleft. It diffuses across to the other cell, binds to the receptors found on the postsynaptic cell, and finally it changes the permeability, therefore the membrane potential of the postsynaptic cell. And if this change is big enough, and it's a depolarization and reaches threshold, then an action potential is triggered of the postsynaptic cell. And the information has gone from this cell to this cell. Of course, later on, this neurotransmitter is eliminated so that a next action potential can generate a next action potential in the postsynaptic cell. As an example, I will go and describe in a little more detail. Please do not attempt to draw the picture. The so-called neuromuscular junction. This junction occurs between a motor neuron and a skeletal muscle. Neuromuscular junction. Junction between the motor neuron and your skeletal muscle. This is what makes you osteopenia. You can see the myelinated axon coming here, branching, losing its myelin sheath, attaching to the axon, attaching to the skeletal muscle fiber. This is the muscle here. This is now, this is enlarged here, and this little portion is enlarged here, where you can see the membrane of the axon with the vesicles containing a molecule called acetylcholine. Have you heard the molecule acetylcholine before? Very good. So the neurotransmitter in your neuromuscular junction is acetylcholine. Here you see the membrane of the skeletal muscle, which has acetylcholine receptors in the on the muscle, so on the postsynaptic cell. Here there is a so-called fibrous matrix, which contains an enzyme, so-called acetylcholine esterase, which is an enzyme that cleaves acetylcholine to acetate and choline. those were just drawings. This is an actual electron micrograph with the axon up here, with the muscle here, with the vesicles here, the fibrous matrix in the synaptic cleft, and the acetylcholine receptors on the muscle cell. This would be these ones over there. So a few words about this acetylcholine receptor. It is a ligand-gated cationic channel built up of 5 subunits: 2 alpha, beta, gamma, and delta subunits. It's referred to as nicotinic acetylcholine receptor due to the fact that a strange substance no one has ever heard of, nicotine, binds to this particular receptor. Actually, this nicotinic type acetylcholine receptor is found all over your brain, and once you intake nicotine stimulates these acetylcholine receptors in your brain, and you get used to having these receptors stimulated in your brain. And once this is taken away, your brain doesn't like that. And this is why it is so hard to quit smoking. Although I have heard some people say that they don't understand why it is so hard to quit smoking, it happened that they could do it in every single day. Kids quit smoking today, and then tomorrow, no problem. So, nicotinic acetylcholine receptor. So, this nicotine actually mimics acetylcholine, can open and stimulate these receptors. This is a very large pore, and as you can see here, it is aligned with different charged amino acids, with negative charges facing the outer and inner vestibule. Therefore, it is selective for cations. Now, normally, sodium and potassium, or even ammonium ion, would be readily go through this channel. So you could ask, why did I say that this is a sodium influx in these channels? Well, ladies and gentlemen, a skeletal muscle has a resting membrane potential close to minus 90 millivolts or so, and even neurons have membrane potential of minus 70 millivolts or so. Much closer to the potassium equilibrium potential than to the sodium equilibrium potential. So therefore, although the conductance for sodium and potassium are the same, the driving force for sodium is much greater there because of the much greater electrochemical gradient. So there is mainly a sodium influx under physiological conditions through these nicotinic acetylcholine receptors. And this sodium influx generates a depolarization on the postsynaptic cell, in this case on our muscle. And this depolarization will then initiate the action potential on the muscle that we would like and use for contraction. So what can we say about this transmission of information? Well, a few things and are listed on the left. I will go through each and every. And on the right, you will see experiments that actually prove that that's the case. The events that happen in the neuromuscular junction are at current through these channels that I have just described, and the accompanying changes in membrane potential. Since this place on the muscle is called end plate, I will be calling the current that goes through these channels end plate current, and the potential that accompanies it has an end plate potential. So the end plate current has a reversal potential around 0 millivolt. One of your colleagues during the recess asked me, why do we call this reversal potential? What is this reversal potential? Well, ladies and gentlemen, reverse means that the direction of the current changes. If the membrane potential is negative, the current is flowing inwards. If the membrane potential is positive, then the current is flowing outwards. So the reversal potential in this case is around 0 millivolt. In case of sodium, the reversal potential is plus 55 millivolts. If the membrane potential is less than plus 55, sodium goes in. This is the direction its chemical gradient is pushing it. If through strange devices and things learned in life physics, voltage clamp, have you heard the expression voltage clamp? Unfortunately, yes. And you make the membrane potential more positive than plus 55, then sodium will go out. So the current, the direction of the current has reversed from going in to going out. This is reversal potential. Okay? So, what else can we say? Well, we can show that this end plate potential is a simple electrophonic membrane potential change. So at the level of the end plate, no action potential is generated. Only an electrophonic potential change, that is, the current goes in and a depolarization is followed. And since this is an electrophonic change, it can be characterized with everything that you have learned for an electrophonic potential change. For example, if you measure further and further away from the end plate, the amplitude of this electrophonic potential change gets smaller and smaller. Of course, it can be summated, it has no refractory period, and so on and so forth. Everything that is true for an electrophonic change. You would obviously ask the question then, where did the action potential in the muscle go? Well, I've been cheating. That is, during the experiment I've been cheating. I've been preventing action potentials from occurring to be able to measure these changes. Normally, this would happen what you see here in case of B. That is, if you stimulate the muscle, then a big electrophonic potential change occurs way beyond the threshold, and the muscle generates an action potential. Actually, this depolarization is so big that in every case, your muscle will respond with an action potential to the incoming stimulation from the nerve. It is absolutely essential that this happens. Just imagine the case that you decide that, oh, I would like to drink, and go and pick up the glass, or whatever cup. But my muscle, even though the nerve impulse is come, won't move. Then I would be standing here and looking at that cup, and that cup would never ever come to my mouth. So the muscle must move if the nerve tells it. Now, in case of a cup, this is not a big problem. But if that's a lion, and I would like to run, and my legs don't start running, now that, ladies and gentlemen, becomes a big problem. So I've been cheating because I've been showing you the case that you see here in case of B, in case of A, where in this case, to get rid of the action potential by suppressing the change in the membrane potential by the addition of a substance called D-glucuronide. What that is, I will come back to in a few slides. C is another toxin that influences this transmission. Let me just say at this point that D-glucuronide acts on the nicotinic acetylcholine receptor, whereas botulinum toxin, coming from this little bacteria Clostridium botulinum, it grows in food that went wrong and secretes this toxin. And this toxin prevents the acetylcholine-containing vesicles from docking. So if you eat this food that went wrong, it's a very bad food poisoning, and you very easily die. This is another substance used in medication called esarin or physostigmine. Physostigmine would be the chemical name, esarin would be the name used in pharmacies. And of course these again were measured in the presence of tubocurarin to prevent them from being very big. Esarin acts on the acetylcholine esterase and blocks the acetylcholine esterase, so the acetylcholine is not removed, so the current is prolonged. Not only organic compounds can influence the activation of this or transmission of information in the neuromuscular junction, but simple changes in ionic composition. What you can see here, two graphs. Again, we are measuring this end plate potential in the presence of tubocurarin, so that they are not too big, so action potentials don't occur. The two graphs are the same, except that this one is plotted on a log scale, this one is on a linear scale. So whichever you would like to look at. You can see that in case of a given magnesium concentration, let's say 2 millimolar, changing the extracellular calcium concentration, making it bigger and bigger, you get bigger and bigger end plate potentials. This is very simple explanation that, remember, steps of involves calcium influx. So if there is more calcium to go in, more neurotransmitter vesicles will be released. However, magnesium can replace calcium in this channel. So if you make more magnesium, less calcium goes in. So at a given calcium, making it magnesium go higher and higher, less transmission of information. The reason I thought that this would be important is probably you have seen commercials in the TV that eat magnesium. Magnesium is good for you. Have you seen this? So please understand that magnesium is very important because ATP you can only utilize in the form of magnesium ATP in all your pumps. So if magnesium is not enough, then problems start to occur. However, if magnesium is too much, the neurotransmission starts not to work properly. So magnesium is just like other things. You should not eat too much from it because if you eat too much, it's not good. This is something that they don't tell you in those commercials. They don't care if your synapses don't work very good. They only care how much of those tablets did you buy. Obviously. So this is just a little pharmacology that you will study in more detail when you get to 4th year, but I thought that some things are might be interesting to hear at this level. So you can in fact influence the release of acetylcholine from the nerves by changing calcium and magnesium concentrations in the extracellular environment. And you can also block the docking of these vesicles by the toxin secreted from that particular bacteria called botulinum toxin. You can influence the elimination of acetylcholine by influencing the acetylcholine esterase enzyme. This is probably the fastest working enzyme in our body. We have so far not been able to find anything that would make it go faster. We have found many things, that make it go slower. I've shown you acerine and pisostigmine, or the pharmacy name acerine. But many pesticides, you know what pesticides are? Things to kill bugs. And more gases act on this acetylcholine esterase. There is one particular film that most of the students usually know, and it was played by Sean Connery and Nicolas Cage. The one when they had to go into the Alcatraz. Remember? The Rock, I think that was the, but something like that, or breaking into the whatever. And they had these little green balls. So, hands up who has seen the film. Not many. No, I just wanted to give you that. It has been explained that in that film that how terrible that gas is, and then when Nicolas Cage gets exposed to the gas, what he does, gives an injection into the heart. Now, please do not attempt to give yourself an injection into the heart. You would have to give it into the ventricles. But it is very hard to stop any of these war gases if one's been exposed to them. How you can do that, I will explain it in a second. After explaining that there are substances that act on the opening of the nicotinic acetylcholine receptor, you can enhance its opening by obviously nicotine, as I have explained. Carbachol is a special acetylcholine analog which the esterase does not block. It can be blocked by certain toxins in the nature. Deoxyribonucleic is a toxin used by the natives in South America. They put this poison onto their arrows. This thing. They take frogs, put them in a bowl, start to boil them. This troubles the frogs, so they secrete this toxin through their skin. And then the Indians put the toxin put their tip of their arrows into the toxin and use that to shoot. It's very effective because it stops the muscles from working. So not only will the animal that gets hit die from the lack of being able to breathe, but it will not be able to run away either. So it makes it easier to find in the jungle. And you don't have to kill by the arrow, you just have to scar. The alpha-bungarotoxin, on the other hand, is used by a snake in Asia, mostly found on the island of Taiwan. So, in order to compensate for the blocking of the acetylcholinesterase, you have to stimulate. You have to block the nicotinic acetylcholine receptor. So if this is blocked, therefore more acetylcholine is present, then you just block the nicotinic acetylcholine esterase, for example, by giving D-tobacurarin. And the other way around, if there's a D-tobacurarin poisoning, what you do is block the acetylcholinesterase so that the acetylcholine is there for longer. So sometimes toxins and poisons act against one another, and as I've said, it's very rare that people use and attack directly the direct transmission of information, but poisoning is such a case. And so is surgery. When in case of a thoracic surgery, you don't want muscles diaphragm from moving up and down, so you block the transmission of information, and you use this guy to do that. And some others, which I have not the time to discuss. Well, this, ladies and gentlemen, brings us to the point that I have to say very few words about information going from neuron to neuron. Very simple. the difference between a neuromuscular junction and the synapse between two neurons is tiny. First of all, the name is different. We call these interneuronal chemical synapses, we make them into two groups. One of them is called the so-called excitatory synapse. And in the excitatory synapse, an excitatory postsynaptic potential, EPSP from now on, develops. And actually, all the characteristics of an EPSP and that of an end plate potential are essentially identical. Non-selective cation channel, depolarization of the postsynaptic cell, usually sodium influx, and of course the EPSP is an electrophoric potential change. So what's the difference? Where the difference is essentially this. That is, the EPSP is significantly smaller than the end plate potential. Therefore, a single presynaptic action potential usually does not initiate a postsynaptic action potential when the information travels from one nerve to the other. In case of the skeletal muscle, information comes, muscle contracts. In case of a nerve, information comes, it not necessarily travels along. Everything else is the same. The neurotransmitter and the receptor might be different. Glutamate, for example. But if there are excitatory synapses, there must be inhibitory synapses. And I will spend 2 or 3 sentences more to describe the inhibitory synapse. Some of the characteristics of the inhibitory postsynaptic potential, IPSP from now on, are the same as an excitatory postsynaptic potential. That is, there is an ionotropic receptor on the postsynaptic membrane, receptor for the neurotransmitter, IPSP is an electrophoric potential change, and so on. However, there are some significant differences between an IPSP and an EPSP. Namely, these ionotropic receptors are selective channels. They are either selective for potassium or chloride. And therefore, instead of sodium going in, either potassium comes out and makes the membrane more hyperpolarized, less excitable, or chloride goes in and again makes the membrane hyperpolarized, or if you wish, less excitable. So the result is that in case of an EPSP, if under good conditions an action potential is developed, if you have an inhibitory synaptic potential, a hyperpolarization develops. This is not necessarily always seen, but the excitability always decreases. So if 2 synaptic potentials come at the same time, we will be talking of this in the next lecture. Not today, but when the next lecture comes. These 2 can add up, and this inhibitory synaptic potential can prevent the excitatory synapse from stimulating the nerve. This is called neuronal integration. This, ladies and gentlemen, is the topic of our